very good morning. This is third lecture in quantum computing. This is a lecture on Introduction to Quantum Mechanics. Here we will discuss about what is qubit, physical implementation of qubit, what is quantum system, linear operator, linear vector space, and Hilbert space. In quantum computing, a qubit or quantum bit is a basic unit of quantum information. In classical computing, classical information bit 0 and 1 are the fundamental units. A qubit is similar to bit, but it has unique quantum properties such as superposition and entanglement. A qubit is a two-state system where both 0 and 1 state can exist at the same time. This allows quantum computer to perform certain calculation much faster than classical computer. In quantum computing, qubit can be described as a two-dimensional vector in complex Hilbert space. Suppose this is a complex Hilbert space, and here the qubit in this Hilbert space is a coherent superposition of the basis state, which means a single qubit psi can be described by a linear combination of these quantum bases ket0 and ket1. These quantum bases are corresponds to 0 and bit 1. So the qubit psi can be represented as linear combination of quantum bases ket1 and ket0. Psi will be equal to alpha ket0 plus beta ket1, where alpha and beta are the probability amplitudes and both are complex number. The probability of outcome of quantum state 0 is alpha square, and the probability of ket1 is beta square, because the absolute square of the amplitude equals to the probability. So according to the second axiom of the probability theory, we can write mod alpha square plus mod beta square is equal to 1. With the two-dimensional Hilbert space, it has 2 degrees of freedom. So any two-level quantum mechanical system can be used as qubit. And here you can see, if you have a two-dimensional system like x-axis and y-axis in classical system, and correspondingly I and j are the unit vectors. So any vector a can be written here as, in the projection of a in x is ax, and projection of a vector in y is ay. Then it can be written as axi plus ayj. And here these are the I and j. Correspondingly in Hilbert space, these are the quantum basis ket0 and ket1, correspondingly unit vector I and j. So we have written psi is equal to alpha ket0 plus beta ket1, and here alpha and beta are correspondingly the projection of this vector in the direction of ket1 and in the direction of ket0. So this psi can be alpha ket0 plus beta ket1, and this can be written as in the form of alpha beta in column vector as alpha and beta. So the representation of qubit in the vector form is like here. So if I'm going to write psi is equal to ket0, if beta is 0 and alpha is 1, then qubit psi will be equal to ket0, and this will be in matrix form as alpha here 1 and beta 0. So ket0 can be written as column vector 1 0. Similarly, psi will be equal to ket1 if alpha is equal to 0 and beta is equal to 1. Then psi is equal to 1 ket1, and this ket1 in matrix form can be written as 0 1. Now physical implementations of qubits, different applications like quantum sensing, quantum computing, quantum communications are using different implementations of qubits to suit their application. The following is the incomplete list of physical implementations of qubits, and the choice of the basis are by convention only. First, if you use photons as qubit and use polarization of light as the information encoding, the quantum basis ket0 can be as the horizontal polarization, and quantum basis ket1 can be as the vertical polarization. If we use number of photons focus state as qubits, then quantum basis ket0 can be a vacuum and quantum basis cat 1 can be the single photon state. In photons, if we use time bin of arrival as qubit, then the quantum basis cat 0 can be as early and quantum basis 1 can be as late. If we use coherent state of light as qubit and information is encoded as squeezed light, then quantum basis cat 0 can be amplitude squeezed state and quantum basis 1 can be the phase squeezed state. And if we use electrons as qubit and information is encoded as electrons spin, then quantum basis cat 0 can be as the up spin and quantum basis cat 1 can be as the down spin. If we use electrons numbers of information encoding, then quantum basis cat 0 can be no electrons and quantum basis cat 1 can be 1 electron. If we use nucleus as qubit and information is encoded as nuclear spin addressed through NMR, nuclear magnetic resonance, then quantum basis cat 0 can be up spin and quantum basis cat 1 can be as down spin. If we use optical lattice as qubit and if information is encoded as atomic spin, then quantum basis cat 0 can be up spin and quantum basis cat 1 can be as down spin. Now, if we use superconducting charge as qubit in Josephson junction and information is encoded as charge and no charge, then quantum basis cat 0 can be uncharged superconducting island. This means a small isolated superconducting region that does not currently hold any net electric charge, and the quantum basis cat 1 can be charged superconducting island. If we use superconducting flux as qubit and information is encoded in form of current, then quantum basis cat 0 can be the clockwise current and quantum basis cat 1 can be the counterclockwise current. And if we use superconducting phase as qubit and information is encoded in the form of energy, then the quantum basis cat 0 can be ground state and quantum basis cat 1 can be first excited state. Now another, if we use single charged quantum dot pair means electrons localization as qubit and information is encoded as charge or electron localization, then the quantum basis cat 0 can be the electron on the left dot and quantum basis cat 1 can be as the electron on the right dot. And if we use quantum dot as qubit and information is encoded as dot spin, then the quantum basis cat 0 can be down spin and the quantum basis cat 1 can be the up spin. If we use vibrational energy states as qubit and information is encoded as phonon or vibron, then the quantum basis cat 0 can be the superposition of cat 01 and quantum basis cat 1 can be the superposition of cat 10. If we use electrons localization in van der Waals heterostructure as qubit and information is encoded as charge, then the quantum basis cat 0 can be the electron on the bottom sheet and quantum basis cat 1 can be the electron on the top sheet. Now, what is quantum system? A quantum system means whose basic states cat 0 and cat 1 form a vector space over complex number alpha and beta. This vector space satisfy the few properties: finite dimension. In conventional, it is infinite, and inner product or scalar product is defined, and this vector space is known as Hilbert space. Hilbert space is a linear vector space over complex number. Vector space is a group under addition and satisfy four properties under multiplication. The two-dimensional Hilbert space with two bases cat phi 1 and cat phi 2. These are the two bases. Like in two-dimensional, we have written this phi qubit as alpha cat 0 plus beta cat 1. Here the two bases are phi 1 and phi 2. Then this quantum system is nothing but linear combination of these two quantum bases. So this quantum system psi, it will be the linear combination of phi 1 and phi 2. So the elements of Hilbert space are nothing but a quantum system or qubit. So we can say quantum system is an element in Hilbert space. So here we have written psi quantum system or qubit in Hilbert space. This is the linear combination of the quantum basis phi 1 and phi 2. C1 and C2 are the probability amplitudes or constant. And if we are having more than two bases, phi 1, phi 2, phi 3, phi 4, these are more than two bases, and there is quantum system or qubit in this Hilbert space, then this quantum system is defined by phi. It will be the linear combination of all quantum bases. So it is the summation of Ci and quantum basis phi I, where Ci is the complex number. This is probability amplitude. So we can say here Hilbert space is a linear vector space over complex numbers whose inner product is defined. So now question is why linear? Hilbert space is spanned by basis vectors phi 1, phi 2, phi n, and any system, for example, spin 1 by 2 system. It is expanded by two basis states up and down. If you have a spin 1 particle system, it is expanded by three bases. So here there are two bases up and down, or you can say cat 0, cat 1. And spin 1 system, it have three bases: spin 1, spin 0, and spin -1. If we have three basis state, phi 1, phi 2, and phi 3. So what quantum system will do? It will go from one state to another state. Means whenever you make a measurement, it will available in any one of the state. For example, coin tossing. When the coin is suspended in air, it is having both state, head or tail. So if I consider head is denoted as cat 1 and tail is denoted as cat 0. So whenever it is suspended in air, it is having both state, cat 1 and cat 0. But whenever it is measured, it will be in any one of the state. So the quantum state will collapse and this will transform into any one of the bases, cat 0 or cat 1. So just like if I am having the two bases cat 1 and cat 0, and in Hilbert space this qubit psi, it is represented as alpha cat 0 and beta cat 1. So if I apply a measurement on this state, it will be either in cat 1 or cat 0 state, or you can say it will be head or tail. So it is making transformation from one state to another, and these transformation are linear transformation, and it will be in any one of the form, beta cat 1 or alpha cat 0. So if you are having psi as the linear combination of two bases phi 1 and phi 2, then we apply the operator, measurement operator on this quantum system or qubit psi. Then operation on a combined system, it will give you the sum of the operation of individual system. A1 operator is applied on the quantum basis phi 1, and A2 the system operator applied on phi 2. This is the simple definition of linear operation. Now, linear vector space. We know Hilbert space is a linear vector space over complex number whose inner product is defined. The linear vector space is a collection of vectors that meet the following conditions. There exists a vector addition operator such that for all cat x and cat y, we have cat x plus cat y, it will be equal to cat y plus cat x. So this follow the commutative and closure property. This can also have the associative property, means cat x plus cat y plus cat z. It will be equal to cat x plus cat y and plus cat z. And there exists a null vector cat 0 such that cat x plus cat 0, it will be cat x. For every vector cat x, there exists an additive inverse minus cat x such that cat x plus minus cat x it will be equal to cat 0. And there exists multiplication operator with scalars like a, b, c such that if I am applying a on cat x plus cat y, it will gives you a cat x plus a cat y. So this follow the distributive property. There is also associative property here. If I am applying a constant a with cat x having constant b, it will be ab cat x. And this follow the distributive property. If this is the combination of two scalars ab and I am applying cat x, then this follow the distributive property. This is distributed in a and b. There exists a multiplicative identity 1 such that 1 into cat x it will be itself cat x, and 0 into cat x it will be cat 0. Now it is time to take a review of three-dimensional space. It is three-dimensional, and here the direction are x, y, and z. And in the direction, if I consider unit vector I, unit vector j, and unit vector k. Now this vector, a, this can be represented as ax into I plus ay unit vector j plus az unit vector k. Here ax is the component of vector a in the direction of x, and ay is the component of a in direction y, and az is the component of vector a in direction of z. So here these are the unit vectors I, j, and k in the direction of x, y, and z respectively. So can you write any vector without these unit vector I, j, k? Answer is no. Now if I consider I, j, k are the basis state, and here in this basis state there are some properties. I dot I, this is 1, j dot j 1, and k dot k 1. This condition is known as normalized condition. And I dot j, j dot k, and k dot I 0. This is known as orthogonal condition. So here these bases or unit vectors I, j, k follow the orthonormal condition, and it is said to be complete. Means no other basis is required. Only these three are enough to represent any vector in three-dimensional space. Now, if it is not complete, we will complete it how? By using Graham-Smith orthogonalization process. We will discuss it later. Now, I am taking analogy between Hilbert space and three-dimensional space. So here in Hilbert space, let three bases like unit vectors in x, y, z direction in three-dimensional. There are three quantum bases phi 1, phi 2, and phi 3. So here we can say H space is spanned by the three bases, quantum bases cat phi 1, cat phi 2, and cat phi 3. If you want to represent a quantum system, just compare to 3D space. A vector is a linear combination of a unit vector I, j, and k. Similarly, any quantum system is a linear combination of three basis states, phi 1, phi 2, and phi 3. So, the quantum system in Hilbert space, it is defined as the linear combination of these quantum bases. So, C1 cat phi 1 plus C2 cat phi 2, C3 cat phi 3. This is the psi quantum system psi in Hilbert space, and here C1, C2, C3 are the probability amplitudes. And here, just like in three-dimensional I, j, and k follow the orthonormal condition, here these quantum bases cat phi 1, cat phi 2, and cat phi 3 must satisfy the orthonormal condition. This means the inner product of phi 1 with phi 1 it will be 1, and the inner product of phi 1 with phi 2 it will be 0. This orthonormal condition we can represent as integration of conjugate phi I and phi j, and this will be equal to delta ij. and this quantity will be equal to 1 if I and j are equal, and it will be equal to 0 if I not equal to j. And this quantity, we can represent this inner product as in the form of bracket notation. So here the complex conjugate will go to bra vector and normal will go to ket vector. So this is bracket notation and this is inner product. So inner product of quantum basis phi 1 and phi 2, or you can say phi I and phi j, it will be equal to delta ij, that may be equal to 1 or 0. It will be 1 if I is equal to j and will be 0 if I not equal to j. This satisfy both orthogonal and normalization conditions, such as in three-dimensional unit vector I, j, and k follow the orthonormal condition. And this is represented as inner product. This kind of notation is the bra notation, and this notation is the ket notation. These are notations, we know the Dirac notation. So here our bases are complete, means no other basis will require to represent a quantum system in Hilbert space. Now, the question is, if psi belongs to Hilbert space, psi is normalized or not? Just in 3D space, if I, j, and k are the normalized condition, then we can say I dot I, it will be equal to 1. And this is known as the inner product. So if phi is normalized, then the inner product of phi, it will be equal to 1 if this is normalized. So this can be written as phi conjugate and ket phi. So if this qubit psi is represented as the linear combination of quantum basis C1 ket phi 1 plus C2 ket phi 2 plus C3 ket phi 3, then I can write this as integration C1 conjugate phi 1 conjugate plus C2 conjugate phi 2 conjugate plus C3 conjugate phi 3 conjugate into C1 ket phi 1 plus C2 ket phi 2 plus C3 ket phi 3. So here I can write this as C1 mod square integration ket phi 1 conjugate and ket phi 1 plus C2 mod square ket phi 2 conjugate and ket phi 2 d phi plus C3 mod square ket phi 3 conjugate and ket phi 3, because this is inner product. And the inner product of, just like I and I1 and I dot j is 0, so this will be equal to 1, this will be equal to 1, and this will be equal to 1. So we have here C1 mod square, C2 mod square plus C3 mod square. And this is the sum of square of amplitude, and square of the amplitude is the probability. So and this summation of this probability, it will be equal to 1. So here we can see that this inner product is equal to 1. So we can say if the quantum system psi belongs to the Hilbert space, then psi is normalized. This is the end of this lecture. In the next lecture, we will discuss about the significance of inner product. Till then, thank you.